All right, everybody. This is where we took off last time. We were talking about protein functions, and we kind of parted ways when we were talking about the protein hemoglobin. And hemoglobin, whenever it is bound to oxygen versus when it's not bound to oxygen. So when it's bound to oxygen, hemoglobin actually absorbs light at the highest points at about 540 and about 580 nanometers. Whereas when hemoglobin is not bound to oxygen, it absorbs the highest at about 560 nanometers. Now, one thing that's worth noting is that hemoglobin or oxyhemoglobin still does absorb light at 560 nanometers, but compared to at about 540 and 580 nanometers, whenever it's bound to oxygen and absorbs those two wavelengths considerably more. Now, this is significant and worth noting because that's actually like these different wavelengths of light that are absorbed are the technology that's used in an Apple Watch or a pulse oximeter, something that as soon as you go to the doctor or you go to if you go to a doctor for a routine physical or if you go to the hospital for something more emergent, one of the things that they're going to do is put a little clip on your finger, and that's going to read your blood O2 saturation. And that's generally like 95% plus, between 94 and 98%, or as high as 100%. Whenever it's getting lower than that, then something significant. The blood that's perfusing throughout your body doesn't have the oxygen that you really kind of need. Now, with that to say, that's the point of this graph over here on the right-hand side of the slide. Now, one of the things that I also mentioned was oxidation of iron from Fe2 plus to Fe3 plus is something that is going to ultimately prevent binding of O2. So this Fe3 heme complex leads to your blood being a slightly more brown color. Now, what this is all referencing right here is heme plus, and heme is your heme is the prosthetic group, hemoglobin, and that kind of combinations, and Fe2 plus, and that combination's ability to bind O2. Now, this right here, this is an important thing that's a little bit different. And I want to make this point so that you kind of walk away understanding it a little bit better. Fe2 plus, the iron heme complex, independent of hemoglobin, can also bind O2. So if you were to kind of isolate heme with iron in the middle of it, that can bind to O2. Well, this combination can also bind to CO, or carbon monoxide. It can also bind to NO, nitric oxide. It can also bind to H2S. Now, the binding affinity that this combination, this Fe2 plus heme, has for carbon monoxide, NO, and H2S is actually higher than that of O2. So what that means is that this right here is more likely to bind, if you had an equal concentration of O2 and CO, this combination is going to go for the CO as opposed to the O2. It has a higher affinity for binding that. Now, to put this all in context, the dissociation constant, or the KD, for carbon monoxide that the iron heme complex has, these rectangles here, and kind of like the heme rings, we're getting a cross-section view of it. That binding of O2 versus carbon monoxide, this has a dissociation constant that is 20,000 times smaller than it is for O2. So its affinity for O2 is 20,000 times lower than that of carbon monoxide. And one of the reasons for that, and sorry, just to go back here, KD, that's your dissociation constant. The smaller that number is, the greater the affinity is. Now, the reason for that, if we look at this model right here and this model right here, well, carbon monoxide binds vertically and not at an angle like O2. So this is actually this kind of vertical or angled binding is kind of similar to when you think about beta sheets in your secondary structures of proteins. We had your beta sheets that are formed as parallel or anti-parallel, and those anti-parallel ones give you straight bonds, and those are stronger, whereas the anti-parallel ones are angled and they're a little bit weaker. So carbon monoxide interacting with the heme Fe2+, well, that's what makes this considerably stronger due to the fact that there's no angle there. Now, when we change this, so this scenario right here is Fe heme plus O2 or carbon monoxide. Okay. Now this right here says the KD for carbon monoxide is only 200 times smaller than the KD of O2 for myoglobin bound heme. Okay, so now it's not just that prosthetic group floating around in space with iron in the middle of it. Instead, we're talking about this combination of MB, myoglobin, plus Fe2 heme. Okay, so what makes this different? Well, situation A versus situation B. In situation A, it's just the prosthetic group and the iron. Situation B, we have the polypeptide, the protein that surrounds this. And if we jump back for a second, this is our heme molecule right here, putting a big circle around it. What's above, or what's to the right of heme? Well, part of the protein. What's to the left of that heme? Part of the protein. If we look at it in this model, well, that heme is in the center and surrounded by a series of proteins or a series of portions of the protein. The amino acids that surround where that iron and that heme are definitely going to play a role in binding affinity just by simply their presence. So what we see is that the presence of that protein, myoglobin in this case, causes the dissociation constant to go from 20,000 times smaller to 200 times smaller. And so the protein, so the addition of the protein basically shifts it so that it's slightly more competitive for O2 to bind than carbon monoxide. And why is that? Well, here's a model showing amino acids depicted in gray here, and where they are with respect to the heme ring or O2 and how that's all coordinated. And those amino acids, those different amino acids are going to obstruct O2's access to that iron. So there's going to be some interference that parts of that protein run. Now, what's important to know, and I always mention this because I think that it's very important. Now I actually have a computer at my disposal. So I'm going to pause. Well, what I looked up was relevant here. So ultimately what this means, this latest item, is that myoglobin has a greater affinity for carbon monoxide than it has for O2. And I think it's reasonable to say that hemoglobin probably also has that greater affinity for carbon monoxide than for O2. And because of that, a small amount of carbon monoxide can outcompete heat or O2 for that spot on heme. So a small amount of carbon monoxide is hazardous. So if you live in an apartment or a home that has gas appliances, it's absolutely imperative that you have a CO detector. Now, I thought that it was a federal law. As it turns out, it's not a federal law, and it's actually not even a state law in Texas. But there are many states in the United States where providing a landlord has to provide you with a carbon monoxide detector. If you live in a place with gas appliances, buy one. They're like $30, and carbon monoxide poisoning really happens, and it is fatal. So spend the $30 or whatever it is, and replace the batteries and everything like that. Okay, so this is ultimately leading to an interaction or a discussion of the interaction between a protein and its ligand. And in order to talk about that, we've got to look at ligand binding expressions, math expressions. So the dissociation of a protein ligand complex can be written simply as an equilibrium. PL is our protein ligand complex, P is our free protein, and L is our free ligand. Now, we have a dissociation constant that has this equilibrium with our products over our reactants. The concentration of each of our products over the concentration of the concentration of our products over the concentration of our reactants. Our reactant is PL. And our product is the free protein and the free ligand. Now, the dissociation constant here is, well, what's the concentration of each product in our ligand over the concentration of our PL or our complex there? Now, in most conditions, the ligand concentration is extremely high compared to the free protein concentration. And therefore, the formation of this PL complex does not really change as the ligand concentration changes. That's in most cases. Now, one of the ways that we look at protein ligand interactions, and that we will look at oxygen hemoglobin interactions, is we look at the percentage of ligand binding sites. So if we take myoglobin has 1 ligand binding site, hemoglobin has 4 ligand binding sites. So what we do is we compare the number of binding sites that are occupied, which is represented by PL, and then we look at that in comparison to the total number of binding sites in solution. So if we use hemoglobin as an example, or maybe myoglobin would be a little bit more clear. And we were looking for the total number of binding sites in a solution that has myoglobin. Well, our free ligand, or our free protein, myoglobin that has not bound oxygen, that has a binding site. And then copies of myoglobin that have bound oxygen, well, those also have binding sites. And so our total number of binding sites is from the concentration of our free protein and the concentration of our protein ligand complex combined. Now, that protein ligand complex concentration, or PL, shows the number of ligand binding sites that are occupied. So you could look at this, what's in the denominator here, as binding sites, or BS occupied, and BS, or sorry, I'll change that to, where's my eraser? I'll change that to binding sites vacant and binding sites occupied. So those are our 2 options there. Now, what we have is this PL, or protein ligand complex, that results from P plus L. We can rewrite this dissociation equilibrium equation, or we can rewrite this as KD 0. We can take that KD is equal to protein concentration times ligand concentration over our protein ligand concentration, and do some algebra to rearrange it. And rearrange it to say, well, our concentration of our protein ligand complex is equal to concentration of our protein times concentration of our ligand divided by our dissociation constant. Okay. Now, where we can take that is we can then take that equation that we just got, PL, and substitute it using this theta. Theta is equal to number of binding sites occupied divided by total number of binding sites in the solution. And we can put it all in context of, well, what is PL? So if we look at this equals theta, take that whole thing right there, and say, all right, well, where can we plug in PL, or where can we plug in the value for PL? This is equal to PL, we can plug it in here. And then we can also plug it in right here. And so in effect, what we've done is we're ending up with this equation right here. Theta is equal to all of this mess, okay? But if you've taken any class where you have to derive any sort of equation, it's a mess, and then it's a mess, and then it's a messier mess, and a complicated mess, and then it's a nice clean equation. And you get to y equals mx plus b. Well, that's where we go very quickly. We can substitute, and then we can simplify this equation to be theta is equal to our ligand concentration over our KD plus our ligand concentration. This equation allows us to express the fractional percent of our ligand binding sites occupied as a function of our ligand concentration. Now, what this is, the value of this is going to give us an equation, or sorry, when this is graphed, we're going to get a very nice hyperbolic curve, which we're going to see in just a moment. Now, this is all in the terminology of protein ligands, or proteins and ligands. We haven't really looked at, well, what's our protein? Myoglobin would be one, or hemoglobin would be one. And what's our ligand? Oxygen would be one. But here, we kind of take what we were just talking about and we pivot a little bit. And when we pivot, now all of a sudden we're going to substitute myoglobin in for the protein, and for our ligand, we're going to use Charles's law to talk about the oxygen concentration. Charles's law says that the quantity of gas absorbed by a liquid is proportional to the partial pressure of the gas above that liquid. In simpler terms, we don't talk about oxygen concentration because it's a gas, but rather we talk about the partial pressure of that oxygen. So using that kind of terminology or that jargon, we can stop saying, we can move away from the theta equation, theta equals ligand concentration, blah, 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 blah. And we can move away from KD and come up with, well, or we can move towards KD where we have the concentration of free myoglobin times the partial pressure of oxygen divided by the myoglobin oxygen complex, our protein ligand complex in this case. Now, what we can do with this and what we can do with KD is we can express the affinity of a protein for a ligand, and we can say, well, KD is equal to 1 over the Ka. And what's worth noting back from probably Gen Chem 2 is that the lower the KD, the higher the affinity of the ligand to the other, or to the protein. So low KD means high affinity, which was why when we were talking about the carbon monoxide, or the KD that heme iron has for carbon monoxide, it's 20,000 times smaller. So the smaller a KD, the higher the affinity. Okay. So now if we go here and look at oxygen binding, this is sort of unique terminology for oxygen binding proteins. Rather than saying theta, instead we use this Y. Y is equal to the number of binding sites occupied divided by total number of binding sites. So putting that into our terms, it would be MbO2, or myoglobin bound to oxygen, divided by free myoglobin plus myoglobin bound to oxygen. We can take that and do some substitutions and ultimately come up with this right here. Y is equal to the partial pressure of O2 divided by KD plus the partial pressure of O2. So the partial pressure of O2 is arguably something that's a little bit easier to measure, which is one of the reasons that we want this. Now, what we can also ultimately come up with is a graph that looks something like this. This is a nice hyperbolic curve. This black line here in this lower left-hand corner is our nice hyperbolic curve. Now, what can this equation tell us? Well, it can tell us what is the fractional percent of oxygen bound at a specific concentration of O2. For example, a fractional percentage. Okay, so fractional percent, if we're talking about 1.0, we're basically saying 100% of those binding sites are occupied. Then 0.8, about 80% are occupied. 0.6, about 60% of those binding sites are occupied. Well, right here, we've got 0.5, meaning about 50% of the oxygen binding sites are occupied. So, this is at a specific concentration or a specific partial pressure of O2, we could say, well, when PO2, when the partial pressure of O2 is 15 torr, what is our fractional percent? We're looking at something like 83%. 83% of those oxygen binding sites are occupied. Now, next up, how do the sites filled vary with the oxygen pressure? Okay, well, as our partial pressure of O2 increases, our fractional percentage of occupied binding sites increases. So if we get up to 25 torr, we're talking about, call it 90% of those binding sites are occupied. Okay, so that would be roughly 0.9. Now, what's worth noting about this, and what's a kind of good metric for evaluating an oxygen binding protein, is we talk about the point of half saturation. So the point of half saturation is our Y sub O2 of 0.5. I'm kind of highlighted this earlier, and that's intentional. When about 50% of our oxygen binding sites are occupied, we want to know what partial pressure it is that got us there. And we can see that that's about, let's call it 2.5 torr. So you could kind of evaluate that and say, well, this protein that we're looking at right here, if you provide a partial pressure of O2 of at least 2.5 torr, this protein has 50% of its oxygen binding sites occupied. You could also say, well, if the O2 concentration or the partial pressure of O2 is less than, 2.5, then less than half of our binding sites are occupied. Another point on this curve that's worth noting is, well, at the top, we've got our fractional percent occupied, 100%. And in this line, this hyperbolic curve, it kind of goes and it plateaus. And it never actually reaches that 100%. The partial pressure is going to continue to go up, but it's probably not going to get there. So this is a realistic view of what an O2 binding curve actually looks like. Now, that 50% mark is significant because that is something that is used to evaluate different oxygen binding proteins. This is known as the P50. And another way that you can look at this is when our PO2 is equal to our KD, then 50% of the ligand binding sites are occupied. The KD for an oxygen binding protein is generally called a P50. So what's worth noting about this and what's worth understanding, what's important to understand about this is that this P50, well, that is coming from the y-axis where we're looking at a fractional percentage, but it's graphical coordinates where we're saying, what is the pressure of O2 that got us to 50% occupied? What is, how much oxygen got us there. So whenever we talk about a P50, we have units for them, or units for a P50, because it's 50% occupied, but what is the O2 pressure? So what's the amount, what's the concentration of O2 that gets you to your P50? So this is the oxygen pressure at which myoglobin is 50% saturated with O2. Worth noting about this is, well, this is similar to KD. A high P50 means you have a low affinity for oxygen, whereas a low P50 means you have a high affinity. Similar to a KD, a low KD means you have a high affinity for whatever substrate it is. A high P50 means you have a very low affinity for that substrate. So those are inversely related. Now, to illustrate this, we've got this nice little graph right here. And this graph shows us basically a P50. And let's just call this wild type myoglobin. MB is the convention for writing shorthand myoglobin. And then this is mutant or mutated myoglobin. Capital M lowercase b. The convention for hemoglobin is capital H lowercase b, HB. Hemoglobin or myoglobin. HB not to be mistaken with the great movie Hellboy, a character called HB. At any rate, so here what you can do is you can look at basically these two different proteins. We have our wild type myoglobin and our mutated myoglobin. Our x-axis isn't labeled other than with PO2, but you know, like any graph, you've got a 0 onto infinity. And that's the infinity symbol. Here we go. I'm getting there. And so as we move from this place right here to this place right here, what's happened to the value of PO2 along that x-axis? It's gone up. So that value has gone up. And so we have a P50 here that is lower than the P50 right here. And the way that these numbers were determined was we look at our myoglobin binding curve, and we basically say, here's our roughly our 100% saturation. Let's cut that value in half. And well, we're going to end up with that. Now let's extrapolate out. We extrapolate out and say, aha, that's where our line intersects. Now let's go down to the x-axis and say, aha, this is our P50, whatever that value is. Now for this next graph, or this next plotted data for our mutated myoglobin, we do the same thing. We say, okay, well, it extrapolates outward, and this is roughly our 100%. So let's cut that in half, extrapolate, extrapolate. And now let's move down to our x-axis. And now this right here is our P50 for our mutated myoglobin. Now between these two, the larger the P50 is, the lower the affinity is. So our mutated hemoglobin versus our wild type hemoglobin. Our mutated hemoglobin has a higher or a lower P50, which means that it has a higher affinity. Our mutated hemoglobin, well, it's going to have a higher P50 and a lower O2 affinity. Okay. Now, these nice hyperbolic curves are really what you see when you're talking about a protein like myoglobin. Now, if you remember, if we jump back for a minute, the structure of myoglobin versus hemoglobin. Myoglobin is a monomer, arguably a simpler structure. Hemoglobin, oopsies, is a tetramer. It's a tetramer. Is this a situation where too many cooks in the kitchen, or what's going on? Do these four different components work in concert with one another for this protein to function really well? And the answer to that is yes. And ultimately what's going to happen is you're going to have oxygen binding curves that differ from one another. So this curve right here, or these two curves, one's black, one's red. The one that's red has a sigmoidal shape. That's your hemoglobin binding curve. The one that's in black is your myoglobin binding curve, and it has a hyperbolic shape to it. It goes up pretty rapidly, and then it kind of tinkers off, and then it plateaus. The hemoglobin binding curve, it doesn't go up very rapidly. It continues to go up, and then it kind of tapers off, and then it goes up a little bit more rapidly, but then it plateaus. Ultimately, these two proteins arrive roughly at the same point, never really reaching that 100%. But in both cases, you can figure out a P50. And so even though myoglobin and hemoglobin have different structures, they both function in the same way that they bind oxygen. These are both proteins that have P50s. Now, looking at these two curves, well, the P50 for myoglobin, something like 4 torr. Whereas the P50 for a protein like hemoglobin, something like 33 torr. So between these two proteins, hemoglobin has a lower affinity for oxygen than myoglobin does. Now, that's like part of the story, because actually the structure of hemoglobin has a pretty big role into its affinity for O2. So one thing that's also worth noting is that, well, hemoglobin has 4 binding sites. Hemoglobin must be able to bind oxygen in the lungs and then release oxygen in the capillaries or in the tissue. If you compare that to myoglobin, myoglobin's in the tissue. It binds O2 and releases it as needed. So these two proteins, they're kind of serving different functions. One's they pick up and drop off. The other one's just they, sort of juggle it, manage it. So I'm going to go ahead and pause right here for the next video.